This presentation on the regression discontinuity design is part of the data science training on causal reason. I am Walter Leite from University of Florida. In these slides, I will show you how regression discontinuity design can be used to estimate the effects of treatments. The regression discontinuity design is a type of quasi-experimental design that does not require random assignment to conditions. It is for a specific situation where assignment to treatment is based on cutoff on a continuous pretreatment covariate. So, for example, if there was a group of second grade children that complete an oral reading fluency assessment, and then children below the 25th percentile in oral reading fluency are eligible for small group tutoring and receive that tutoring, and then at the end of the year data is collected on all children. That would be a regression discontinuity design. So there are several situations in education where decisions about the policy or children or students receiving program are based on a cutoff on a continuous measure. And all these situations, the regression discontinuity design can be used to estimate the effect of the intervention. So this is a schematic of the regression discontinuity design. Note that it requires two measures for the whole group, one prior to the treatment, then assignment based on a cutoff, and then another measurement, which would be the measure of the outcome. Now, although it shows here as pre-test and post-test, the pre-test does not need to be the same measure as the post-test. The logic of this design is that individuals that barely pass the cutoff and barely do not pass the cutoff, they are very similar. The difference between them is just due to measurement error. Therefore, at the cutoff, it is like you have random assignment because the differences between those two individuals are randomized through the measurement error. Now, therefore, the regression discontinuity design does not estimate the average treatment effect across the entire sample like an experimental design would. It estimates the local average treatment effect, or Leite, which is the average treatment effect at the cutoff. It requires an assignment measure. It does not need to be the same as the outcome measure. It can be a complex variable created by combining multiple measures. It can be several cutoffs where individuals can have, for example, they're eligible if they meet this criterion and this criterion and that criterion. Okay, and the cutoff needs to be established in a way that that it doesn't the cutoff do not affect the scores themselves. In other words, the measurement it first happens and then the cutoff is applied to that measure. So the regression discontinuity design has several practical advantages. One is if a researcher is offering intervention, the researcher can offer the intervention to individuals that need it the most, versus the experimental design where the control group and the treatment group will both have similar proportions of individuals that really need the treatment and that don't need the treatment as much, right? So the regression discontinuity design has that advantage that you are focusing on giving the treatment to those that need it the most. So it's very ethically attractive. Now, it's also interesting because if you were evaluating a policy like a state policy, you can use decisions that are already made by policymakers that result in a regression discontinuity design. So, for example, in the state of Florida, decisions about who need which early childhood centers, which teachers in early childhood centers must receive certain professional development activities are based on testing mandated by the Florida Department of Education, and there is a cutoff that determines who needs which teachers need additional professional development and which is don't. So if you obtain secondary data, you can evaluate the effectiveness of that particular policy of mandating professional development to teachers that do not meet a certain cutoff. So this is, in the absence of treatment, this is what would look like. There is a clear continuity between children below the cutoff and children above the cutoff in the relationship between assignment measurement and post-test score. Now, after treatment, you would expect a discontinuity. So here, this is an example where once the treatment is received, the children in the treatment group score lower. Like, so for example, let's say it's a measure of inattentive behavior, right, which you would want the children to score lower, and that happens after the intervention, and it generates a discontinuity, which is the treatment effect. So in terms of internal validity, which is the ability to make a causal statement about the intervention, the regression discontinuity design is as strong as randomized experiments because it controls for selection bias. That is no possibility of omitting the confounder, given that the assignment at the cutoff is similar to random because it's due to measurement error. Now, the threat to internal validity here would be something that happens at the cutoff that would jeopardize the inference about that discontinuity. So, for example, if there is attrition around the cutoff, that could be a threat of validity. The disadvantage of the regression discontinuity design is that it doesn't have as much power as an experimental design. Actually, that is the power with an experimental design is much larger. You would need 2.75 times the sample size with a regression discontinuity design to obtain the same power as a randomized experiment. Now, you would also have to make sure that you exclude all the reasons for discontinuity that other than the treatment effect. In terms of external validity, which is the ability of the conclusions of the study to generalize, the regression discontinuity design has weaker external validity than the experimental design because the conclusions only generalize to the cutoff. In other words, when you estimate the local average treatment effect, is the treatment effect at the cutoff, so generalizes just to that specific cutoff. If you change the cutoff, you will have to estimate another local average treatment effect for a different cutoff. In contrast, an experimental study estimates the average treatment effect across the entire range of the sample. So the analysis for a regression discontinuity design can be quite simple. An uncover model can be used to estimate the local average treatment effect. So in this model here, we have the outcome y as a function of treatment t plus the cutoff x, the assignment variable, right, centered around the cutoff xc. And this is the simplest model. However, it does not. It assumes that the relationship between the assignment variable and y is linear. Therefore, it makes a strong assumption here of linearity, and I will show that there could be no linearity between that relationship, which would lead to bias if it's not modeled. So the regression discontinuity design, you're estimating the local average treatment effect, but you're also estimating the intent to treat at the cutoff, which means that the effect you are estimating is the effect of offering treatment at the cutoff, regardless of how well participants complied with that treatment offered. As you saw in the ANCOVA model, we center the assignment variable around the cutoff, and that centering is critical to allow the interpretation of the coefficient of the treatment variable as the local average treatment effect. So here is an example where there is no linearity in the relationship between post-test and assignment variable, which gives an impression of a treatment effect when there isn't any. And to be able to control for that, you would want to model the relationship in an absence of treatment. So here is a model where that would be appropriate for the data shown in the previous slide, where it's a regression model with quadratic and cubic terms, modeling that nonlinear relationship between y and x. You could also have an interaction here. The slope of the regression or post-test on the assignment variable changes about after the cutoff, and this needs to be modeled, or else you also will obtain a bias estimate of the local average treatment effect. So in this case here, we've modified the model by including that interaction would solve this problem. So this model is expanding on the ANCOVA model, where we also add the product of treatment and the assignment variable to capture that interaction term. Now, one thing to keep in mind with the regression discontinuity design is that it assumes that the relationship between y and the outcome and the assignment variable x, in the absence of treatment, is modeled correctly. If you model it correctly, you obtain an unbiased estimate of the local average treatment effect. If the model is underspecified, so it doesn't have the correct terms, it doesn't include nonlinear relationships or interactions, you get a bias estimate. However, if it's overspecified, your estimate of the local average treatment effects is still unbiased. Therefore, there is an incentive here to over-specify, to protect against bias that comes from misspecifying the model. So this would be a more typical parametric model for regression discontinuity design. Note that this model has interaction terms, and it also has quadratic and cubic terms and interactions involving the quadratic and cubic terms. So it could be overspecified, but it will protect against misspecification, and you could do backward selection by eliminating non-significant terms after it's fit to the data. It's also possible to use local linear regression to estimate the local average treatment effect. So local linear regression works by dividing the data into sections based on thresholds and fitting regression equations to that section of data. So it's a series of regression splines. So it's a type of smoothing where instead of having a line, you have these curves created by the series of regression splines. The challenge here is to obtain the right bandwidth for dividing your data, and the smaller the bandwidth, the less data you have within that range, which will increase your standard errors. So there is a trade here between bias and efficiency. The small bandwidth will provide less bias, reduce the efficiency. Larger bandwidth may lead to bias because you are missing some nonlinearity, but it's more efficient. So here is a plot showing relationships between bandwidth and efficiency. Okay, so for example, in this first one, the bandwidth is 50, the treatment effect is 5.24, the standard error is 0.61. So this looks very linear, looks just like an ANCOVA model. As you reduce the bandwidth to 10, the treatment effect changes, the standard error increases because you're losing efficiency, but you can see how it gets more curvature. Then with a bandwidth of 5, treatment effect changes, the standard errors change even more. And you can see how it gets, there are more curves, and with a bandwidth of 3, even more curves, and the standard error is even larger. Right? So the trick here is to select a bandwidth that there's still enough data to provide reasonable efficiency. And here's some references for regression discontinuity design. That is a very well-developed guide by Bloom. And then the second article is an example, and the third article provides some of the challenges.